So first speaker is Ian. Ian just graduated a couple of months ago, obviously with a PhD in nuclear engineering, and also they had a designated emphasis in computational data science and engineering. And Ian had the unfortunate experience to work with me, so please, thank you.
Hi, so I'm Ian. Thank you for the introduction. Max was my advisor. I also worked a little bit with Lee on some of my projects. For some more context, I also did my undergrad at Berkeley in nuclear engineering as a transfer student, and I worked at Kairos Power for a year and a half between undergrad and grad school. I'm still figuring out what's next, so I don't have anything super exciting to share yet, but you will all hear about it when that happens. So I'm going to be giving you a summary of my dissertation work, namely just the first 3 chapters, because I kind of had a lot of different projects that covered a lot of ground. This work revolves around pebble bed reactors specifically. So that's the measurement of the fuel as it comes out of them, and how to use those measurements with the operation history to control the reactor effectively. So I'm going to give you an overview of pebble bed reactors, and then we're going to get into a new measurement technique before finally talking about operation simulation. Cool. So let's get started. So many of you probably aren't reactor people, so I'm going to give you a quick rundown on what makes PBRs different. So as their name implies, pebble bed reactors have hundreds of thousands of fuel pebbles that are actively circulating through the reactor core. This is great because it enables online refueling, but which is a huge selling point because static reactors, it's like you have to shut them down, it's expensive, it costs millions of dollars. These reactors also feature coolants other than water, so you might have helium gas or a molten salt like FLiBe. This is good because it enables higher temperatures and lower pressure operations, so you get more safety and thermal efficiency. Each of these fuel pebbles has tens of thousands of fuel kernels inside of them, which are great at retaining fission products at high temperatures. So one requirement with having fuel that is constantly circulating through the core is the ability to measure them and know when they're used up. That is, like the fissile material is depleted. If you don't replace your fuel pebbles over time, the reactor will eventually become subcritical and stop producing power, which isn't great. So across different designs, a pebble usually comes out every 20 to 60 seconds. Ideally, you want to be able to measure pebbles as fast as they come out, so that way you don't have to operate with extra fuel or use multiple detectors. You don't want to have any operating constraints from your detection system. So this measurement process needs to be rapid. Generally, when you're doing burnup measurements, you use cesium-137. It's because it's a very long-lived fission product, especially relative to the operating time of the reactor, simple decay and production pathway, and an intense gamma line at 661 keV. Now, with fuel assemblies, this process is pretty easy because you can just let the fuel assembly decay for a while before you measure it. However, with freshly discharged fuel pebbles, they're extremely radioactive. And they might decay for a little bit in the defueling chute, but overall, the count rates that you're getting are extremely high. And that can cause dead time, that can cause Compton scattering, that can mask the cesium peak. There can also be crowding in the energy range around 600 keV. So it's not easy. You need a lot of shielding and distance. As an example, here's a synthetic high-purity germanium spectrum that I got from a Sandia report on MCNA. So this is their own preliminary work, but you can see here that the count rates are in the hundreds of millions. And even the software that they use, I think this is a Gadger simulation, it lists a 100% dead time. Granted, this is not an optimized setup, but it just kind of illustrates the difficulty of this measurement problem. Typically, high-purity germanium detectors are operated at tens of thousands of counts. There are some specialized setups that can break 1 million, but there are some compromises there. And you might be wondering, what can we do to make this easier? This brings us to the first half of my work, where I explored the use of bent crystal diffraction spectrometers for burnup measurement. So BCD spectrometers, they basically act like energy filters for gamma rays. You have a crystal, say silicon, it's either grown perfectly or it has some controlled amount of defects in it in the case of mosaic crystals. You take the decay gammas from the fuel and you collimate that as a beam that's directed on the crystal. When it hits the crystal at a certain angle, only gammas that are within a very specific energy range are going to diffract constructively and be focused on a detector. This is called Bragg's law. It's not new technology. This has been used in nuclear physics, data measurements, astrophysics. It's big in like beamline synchrotron work. So my work introduces it to the domain of fuel measurement and continuously fueled reactors like PBRs. We actually got a provisional patent on the process, which is fun. My focus with this work as it pertains to my dissertation was the design and the simulation of these instruments applied to PBR. So we're going to walk through a very high level the data generation process, and then we're going to get an idea of what's possible using these spectrometers. So I'm not going to overwhelm you with the data generation because that could take like 10, 15 minutes in its own right. We're going to keep this high level. So first of all, we used HXF, which is a depletion tool developed here at Berkeley, and we used that to simulate the PBR core. This gets us data for individual pebbles. The model that was used for this was the generic FHR, which is Kairos Power's benchmark design that they released. It's a fluoride salt-cooled high-temperature reactor. In this design, pebbles make around 8 passes through the core before they are fully used up, on average. With HXF, for each pebble, we get the fuel composition, so that's all of the fission products, the actinide inventory over time. We get the average pathway that the pebble took, the residence time, the number of passes, as well as the fast and thermal fluence. Then I use Serpent to generate the gamma spectrum for each pebble after it decays a bit in the defueling chute. I used a day and a half because that's about what you would expect to see in practice. With these gamma spectra, highly. No, it's fine. I looked at the different emitted gamma rays coming from the pebbles, and I used data science techniques to figure out which ones correlate the most with the pebble history parameters that we care about. So unsurprisingly, this includes cesium-137. You get some shorter-lived nuclides like neptunium-239, lanthanum-140, promethium-148. The isomer for that was pretty useful because it has a higher plutonium fission yield compared to uranium. And then cerium-144 is a medium-lived nuclide. So measuring these things, we kind of get like a good view of the pebble's history at different timescales. For each of these nuclides, I found a suitable decay gamma for bent crystal measurement. So ideally, you want something that's high intensity, ideally low energy, like 10 to 100 keV is best. We have to push it to the limit a little bit with the cesium gamma. And it also can't be crowded by other gammas. So if the two gammas are completely overlapping in energy, you're not going to be able to resolve them even with perfect energy resolution. So with these gammas in mind, I used Shadow 3, a ray tracing code for beam lines, to design spectrometers for each gamma, since these are static instruments. And it's worth mentioning that each of these designs, they feature a shielding in front of the detector with a narrow slit. And the benefit of that is because gammas will diffract at different angles based on their energy, you can use that slit to even further narrow your energy range and get better energy resolution and reject more things. For each of these spectrometers, I determined the energy filter curve as well as the total efficiency of it being detected. And I used that to weight the spectra for each pebble, and we get something like this. For almost all of the gammas, you could completely isolate the gamma that you care about. For cesium-137 at 661 keV, there's still a lot of other gammas. Unfortunately, the reflectivity of this instrument goes down as you get to higher energies, so you do have to compensate with a wider filter. That's all to say, I used GADRS to verify that even the spectrum that we're seeing, this coarsely filtered spectrum that we're seeing for the cesium instrument, you can still resolve the gammas that are making it through. And that's more of just a check. And the other ones, you can just use scintillators. You can use lanthanum bromide or something like that. So now we have synthetic spectrometer signals for each pebble. I trained machine learning regression models on these signals to predict the pebble properties that we care about. And I compare this to the ideal case where we have like the simulated concentrations and we're using that as input. And you can see that the R squareds are pretty comparable. I also put the error, the absolute error associated with it. With an error of about 2% on burnup, that means that you're very rarely misclassifying pebbles that are at the burnup threshold, which is really good. The other predictions are useful for things like safeguards or characterizing fuel failure, stuff like that. So all in all, this work demonstrates that bent crystal spectrometers are great for burnup measurement. Their signals are useful for regression models that can predict pebble properties that otherwise you would not be able to get. And future work would include design optimization that has like relevant constraints with the footprint and the cost, as well as some experimental verification of the designs. So next, I'd like to take a step back and look at the bigger picture with pebble bed reactors as we move into the third chapter. I'm going to kind of hurry a bit here. PBR operation is very different from light water reactors. Your in-core measurements are much more limited. You don't have direct flux measurements. Reactivity control is also very complex because the different controls affect your reactivity on different timescales. This makes accurate dynamic modeling very important. If you're looking at the different reactivity effects, like you have control rod movement, which is it's going to affect your reactivity near instantly, whereas power changes can be a little bit more delayed, like you have the immediate temperature feedback, but then there's also the time it takes for the xenon to reach equilibrium. Changes to pebble circulation and the burnup limit are a little bit more subtle and take some more time to manifest. Meanwhile, if you're changing the ratio of fuel pebbles that you're inserting, so using different enrichments or using graphite pebbles, that's going to take a few months to fully propagate through the core, while having a large impact on your reactivity and your excess reactivity. And finally, fuel depletion burnup, that's going to be the longest term reactivity effect that happens over months. So one way that you could capture all of these different time-dependent physics is through time series analysis. Specifically, my work looks at the use of a long short-term memory network, 2 minutes. They're a type of neural network that basically keeps memory of the inputs, like you give it a sequence. And so if you're gradually changing the fuel power or the fuel insertion mixture, it's going to keep track of that over time. This model, on the testing data, which I simulated a bunch of different operation scenarios, it performed very well, even on sequences that it completely hadn't seen. And one of the big applications for this work is for running in optimization. So reaching equilibrium with pebble bed reactors, there's a lot of different ways you could get there because of the interdependent time dependence of all of the controls. And what I did is I used the LSTM to control my core simulator and moved it towards full power. And every time I had it predict what the impact on the reactivity would be from changing things and made sure that it would stay critical. Granted, there's a lot of error in the beginning, like it should be zero reactivity, but every time I run it, I also generate more data that I can retrain the model with. So it's a self-refining process. It gets faster and more accurate with each run. And this is still kind of ongoing work for one of the papers I'm working on, but yeah. So to wrap things up, this work has shown great promise for LSTMs in predicting reactivity and also the core power distribution. There's some future work with thermal hydraulics coupling, as well as using different fuel enrichments. Also more machine learning work in terms of adding features, trying different models. But yeah, I'd like to acknowledge my dissertation and qual committee, the people who mentored me while I was at Kairos, the friends I made at Berkeley, the different organizations on campus who helped me, and my family. Thank you all for listening.
One question for Ian?
We also don't have to do a question. You can talk to me after all you want.
Okay, we can do a question after. Thank you, Ian.
Thank you.